Hey guys, this is Parth from FTC Team 7477 Super 7, and today we'll be talking about the actual implementation of a PID in FTC. And we're going to be applying a PID to a use case of an ARM motor first. So we're basically going to be imagining we have an ARM motor and want to move it to a given position using a PID. Now, we've talked about run the position in this tutorial series before, and that's basically how you can move using the built-in SDK, move a motor to its given position using a simple built-in command given by the FTC SDK. And this works, and it's not a bad idea to use for rookie teams, or even if you're in a rush and need to get something. It works. It works well. The only problem is that sometimes it can be slow, and oftentimes you see the problem here, especially in ARMs, where you really need to tune. Run to position works on a PID, and the problem is it's a badly tuned PID because it's not tuned for your system. It's the value is already set by the SDK. So when using an ARM, oftentimes I don't know, you'll see problems where it goes to the position and just wobbles back and forth because the PID is not well tuned. So we're going to be walking around how to implement a custom PID that you can tune yourself for an arm movement, and then in the next video we'll go on to show how you can actually use this for movement of the robot. So we're just going to get started and define our function. And it's going to be, I'm just going to call it arm to position. Again, imagining we have an arm. Now there's a couple parameters that we need to declare in this function to get it to work. First, obviously, you want to declare the arm motor that you're using. You can just simply do this by initializing a DC motor. Let's call it arm. And then what next, you want a target position, right? So I'm just going to declare an integer position since the reading I'm going to be getting from the motor is ticks, and the encoder ticks return integers. So I want to declare an integer target position. Now is my coefficients. So the coefficients are basically the things that you tune yourself, and they are the P, I, and D. So they are going to be double since it's a double coefficient, and we're just going to call it KP, KI, and KD. And you'll see why I'm calling this KD in a second. And then the last thing is when you're running the PID, it runs in a loop. And when I run a loop, I always check if one of my conditions for the loop to run is if my op mode is active. And this prevents the program from crashing or something if you stop it while the arm is moving. It's a nice failsafe to have, and it's a good practice to use. So I'll show you how this is used in a second, but we'll just declare an op mode variable for now, which is basically showing an op mode, and we have to import that. Okay. So we have all of our targets declared. Again, this is the actual motor, the arm motor. This is our target position. These are our three coefficients that we'll tune. This is the op mode variable that you'll see how it's used in a second. Now, our first thing is we first want to declare timer, and this is going to be useful in the integral calculation. So the I part of the loop, as well as the D part. So what that is, how you declare a timer in FTC, we've talked about this in a tutorial series, is just elapsed time, timer equals new elapsed time. Okay, we're just import the class. Now, we're going to set a margin of error. And what that means is, for example, in this case, I'm reading ticks. So how many ticks, if I give it a target position, within how many ticks do I want to be? You don't want to set this to 0, because if you set this to 0, the robot will oscillate around that point and it won't stop the PID loop until it gets exactly that position. So you're going to get a very wobbly movement. I like to set this to around usually 3 to 5 ticks. So I'll just make it 3 for now. Okay. We're going to call two variables called previous time and previous error. And this will be used in a loop to basically, the I and D part of the PID loop rely on the current time and the current error, as well as the previous time and previous error, because they're basically determining the accumulation of error as well as the rate of change. So to determine the rate of change, they need to know the current error as well as the previous error so they can see how it changed. So that's why we also need to store the previous time and error. Now, we're going to declare our variables, and the way this loop works is, remember we talked about how the motor power will be P plus I plus D. So the value calculated from the P part of the loop, I part of the loop, and D part of the loop. Now, the important thing is not to get these variables, the pi and d, confused with the kp, ki, and kd. The kp, ki, and kd are the coefficients that are constant once you tune them. They are what you tune. The pi and d are the actual powers that you'll be adding up to feed the motors. So basically, you can think of the kp as your input and then the p as your output power. The ki is your input, and the I is your output power. The kd is your input, and the d is your output power. So we're going to declare our p, I, and d variables, and these are going to be doubles as well. And let's just set them all to 0 for now. Okay. And finally, we'll just set a power double because we're going to want a power where we add everything together. And now we can start. So our first clause is basically while the motor is not at its target position. So how can we check this? And that is while the absolute value of the difference between the current position and the target position. Here's how we can do that with FTC coding. So math.abs for absolute value. And we want our current position, the difference between our current position and the target position. So the target position is what we inputted, the parameter target. And again, we can easily get the current position of the motor just by calling arm.get current position. Arm.get current position. Okay. And we'll say while this, we basically want this error to be within our margin of error. So while this is greater than 3, we're going to operate the PID to get it within that range. Again, we talked about using the op mode as a failsafe. So basically what this is doing, I'm just going to check if my op mode is active. This is not a requirement, but I recommend it. And all you need to do for that is so this is basically specifying that I have a op mode, that's a linear op mode, and I'm checking to see I'm only running this loop while the op mode is active. And I know that can seem kind of redundant because once you stop the program, the whole code stops anyway, but oftentimes you'll get some errors or some catches, and it's just best to use this in here to avoid any potential problems. Okay, so now we have the setup. We're saying while the motor is not at its target position, we're going to run the PID. And how are we going to do this now? Okay, so first we want to get the current time at every loop. So every loop we want the current time that has passed in the movement. And we can do this just by calling the timer. And for an elapsed timer, you just need to call whatever unit you want. We're going to use milliseconds. We also want the current error. And again, error is current position minus target position. Current position minus target position. So our target position is simply target, and our current position, again, is just arm.get current position. This will return our error, similar to what we did here. This is our error as well. Okay, we have the setup to start the PID now. We're going to start with a proportional term. The proportional term is the simplest and most intuitive to understand. It is simply applying a power that is proportional to your error. All that means is that we will set P equal to Kp times the error. Again, P is the power output. Kp is a tuned coefficient that you will tune of your PID. And again, error is simply the error. So, intuitively, as the error gets smaller, the Kp stays the same, so the P will get smaller, and eventually it'll reach 0. So that is how the PID works. As the error gets smaller, this as the error gets smaller, the power gets less. And honestly, a P loop works in a lot of cases in FTC. You can simply use a P loop in a lot of cases and be fine, but we are still going to walk through the other components. So this is the integral error. And the way you do this, I'm just going to write the calculation out for you. It's accumulation of the error. So you're looking at, so if you're not familiar with calculus, it might be a bit hard to understand, but you're basically looking at the accumulation of the error over time. That's what an integral is. So the way you do this is you take your tuned ki constant and you multiply it by your error times your current time minus the actual I. So this is basically accumulation of error. And that will calculate your I power. And one thing that, since the integral coefficient accumulates over time, you want to take care of something that we call integral windup. And it's basically over a long course of time, the integral error could wind up and eventually have a significant effect on your PID. Say this keeps going up, eventually you might get a bigger power and it will throw off your PID loop. So the way we do this is we set a max I and a minimum I. So I'll just set that up here. And I'm just going to set it to our arbitrary values. I like to keep it at, or this is just random values, but I'm keeping it at 0.2 and negative 0.2 for this video. So basically this is just a basic coding principle. If I is greater than max I, we'll just set I to be equal to max I. Or if I is less than min I, we'll set I. What this is basically doing is it's saying if the calculation of I is greater than the maximum, it's just bounding it, right, to the minimum and the maximum. So that's the integral error. One thing I'm going to say is that I would not recommend using the integral error. It can honestly just lead to a pain in tuning, and honestly, it does not improve the loops, and it has potential for tuning and messing up your loop. So I included the integral component in this video, but in future PID videos regarding movement and stuff, I will not be including the integral because it's not recommended for use in FTC just because it's small scale. So the movement the robot does over the small amount of time is not really necessary of an integral component. So really when I run on my robot, I run PD loops all the time. I run PD loops for movement, not PID loop. But we'll still be going through the whole PID loop just for your knowledge. Okay, so now the derivation error. And this is actually useful. So the P and D are pretty useful. So the way you calculate this, again, you start with D, which is your power output, and your coefficient KD. And this is simply calculating the rate of change of the error. The simple formula for rate of change is the current error minus the previous error over the current time minus the previous time. So as you can see here, the P component is proportional to the actual error. The D component is being multiplied to this thing, so it's proportional to this thing, and this is so directly proportional to rate of change of error. And this is directly proportional to the actual error. So this is basically saying how fast is your error changing and how do I compensate for that in my robot speed. If my error is changing very, very fast, it'll slow me down, right? Now we're done with the actual logic of the PID. Finally, we just need to incorporate the PID in the power. So boom, we have PID in power. So we're just adding the three. Remember, make sure you're not doing the KD, KI, KP, because remember those are constant coefficients that you're setting. And you're adding the calculated powers of PID. And then we can just simply set the power to the calculated power. At the end of the loop, you also want to save your values for previous error and previous time that you're using for the derivative calculations. And the way you just do that is just set your previous error to the current error in this loop and set the previous time to the current time in this loop. So this is it. This is our implementation of PID loop for the ARM. And this is the beginning base of the applications of PID in FTC. The actual scope of usage for a PID loop in FTC is huge, and it's vital to learn for effective programming. So in the next videos, we're going to dive into something called a feed forward, which is used to compensate the effect of gravity on your ARM or slide system. So really, we're going to learn how to run a PID F loop and also how to use PIDs in robot movement. And again, from now on, I'm going to be only using the P and D parts of the loop, as there is really no use for I in FTC. So thank you for watching this video. I hope you learned a lot about PIDs, and if you have any questions, just drop them in the comments, and see you next time.